Good morning, everyone. I am recording this video because I could not complete the longest palindromic substring in the classroom yesterday. So I thought I'll take a fresh breather and go through this algorithm with you right now. So hence recording this video. So there are some assumptions in this video. As I mentioned yesterday, here is the example that I'm going to go with. So ABA, CABA, CABB. All right. So let's say here is my palindromic substring. So there are some rules in here just to, or actually some terminologies. So we're going to have a bunch of variables. So C will be referred to as the center. L is the left of the longest palindromic substring that we have found so far. R will be the longest right-hand side. And then I will be the index that we will use to navigate through this, right? So for example, if the center was at C, the L would be here and the R would be here. That's just the notations that I would like you to understand. And also in this case, we want to consider this as of a length 3. That is the longest palindromic substring length that we have found so far. But later on, but the real longest substring for this specific problem is this. Just so you know, where the center would be here and the L would be here and the R would be here, right? That's the end goal. And the I would land here at the point in time. So now that we know what these all means, I also want to kind of rejigger the formula that I was talking about yesterday in the classroom. C minus J, let's say J being one of the indexes somewhere here. Let's say J was here, for instance, and this would be J prime, right? So C minus J would be same as J prime minus C. I hope you understand that. That means that this distance is same as this distance is what we're talking about. So basically the mirror index of J is going to be this formula, which is 2 times C minus J, which is basically bringing the C to the other side, becomes 2C. And it will be plus J, right? No, it'll be minus J because the minus cancels out. So this is the formula that I will end up having in the code later on, but I just want you to know that this formula, this is basically saying that the mirror on either side, the length of the mirror on either side is the same. So now let's come back to the algorithm. When we move I, this index I, from left to right, we try to expand the palindrome at each eye. That's our goal. Like, when I'm here, I want to try to expand the palindrome. So what does expanding mean? Expanding means that I want to calculate or store the length of the expansion to the left or to the right in a new array. So we're going to create a new array, and we are going to be storing the length of each palindromic substring that we have found so far. So think of this as my P array. This is the array that I want. So if you kind of were to think about the indexes, let me undo some of these things. So I want to keep a little bit clean here. So let's imagine we have, going back to this original string that I've got. All right, there we go. Now let's assume that we have this, and now I have an array that I create in the bottom here. And we have indexes for this, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. Those are the indexes of the array. So this is my P array. So at index I, if I were to here at A, the length of the palindromic substring would be 0. The expansion length is because there is nothing to the left or the right. If I were at B, the length of the palindromic substring to the left or right would be 1. Basically, in this case, the left, right, is 1. When I come to A, you see the B does not match with C. So I end up getting the maximum the expansion length is 0 because I could not find a match between these two. So there is no palindromic substring found. When I get to C, if you index were at I here, then you would look at A and A here, that's 1. Now you come back to B and you find the mirror there, and then you come back to A and you find the mirror there. So basically what we're saying is at this point, the L would be here, the R would be here, right? And then the center would be at C here, and this would be of length 3 now because it's expansion length at 3. Now the question is, when I'm at index I equal to 4, and what will be the value, basically, right? That's the goal that we are trying to find. This is where I left off in the class yesterday with the 2 points. I mentioned 1 point, but that's where I got a little bit sidetracked. So as long as index I, so now index I is here. Remember, so far the center is here The longest length is to the left, the longest right length is here. Now my index is moved to this one, the string A or the character A, right? As long as the index I is less than R, right? Rather than naively expanding my I, we want to know what is the minimum expansion length. Let's just start with that. What is the minimum possible expansion length that I can see at index I without having for me to go back and forth? That's our goal, right? So we can expand on PI and see. So instead of doing from the start, why don't we check the mirror I prime? So rather than actually me doing this, I would check the mirror of the I prime. So as you can see in this case, P of 4 at a minimum should be equal to P of 2. So remember P of 2 is 0. So that's our first assumption. So this could be 0. But to prove the point, you see, I can go look at B and C and it is 0, right? So that makes sense. So this will still remain at 0. But if I were to take a different string, just to give you another idea, so I mean, in this example, this will be 0, just so you know. But if I took another string, let's say I had ACA, CACB, something like that. And, you know, until now, if you were to think about this, if I were to be here at this index, right? Then you can imagine, because remember, this would be 0, this would be 1. At this point, this would be 2, right? Because you're gonna have these two. And when you come to here, this would be 1, 2, yeah, it'll be 1, 2, 3. It'll be 3 at this point. So it'll be here. So now the question is, should my I be same as I prime? So as you can see, it is at a minimum. In this case, if I were to look at my I prime here, in this case, if I say it is 2, but really it is not 2. You see this, right? Because it is 1, but the A and the B does not match. So you see what I'm saying is there is possible two formulas. Either it is a minimum where I can say P of I is equal to P of I prime, but there is one more case. If I is still less than my index R, right? So which means if my palindromic at index I or I prime, if you think about I prime, if I prime expands beyond the left boundary, remember the left boundary is here, or if my I expands beyond the right boundary, then the minimum possible expansion length in that case could also be R minus I. Okay, so what that means is, sorry, here it is not, L is not here, L would have been here, sorry, L would have been here. This would have been a L for this example, and this would have been the R for this example. So what we are saying is there are two possible formulas to consider. The thing is, ideally, you could start with this. My P of I's value should be equal to my P of I prime's value, right? But there is also another case. What if I still is less than my R value? There's a possibility that P of I could be just R minus I, right? Because if I prime still expands beyond L, or if I expands beyond R, that possibility still exists. So really what we need to say is the P of I value should be the minimum between these two formulas, basically. You get it? Between P of I prime and this formula, which is R minus I. So you pick one of the minimum of the two. So if I come back to this formula, the I prime value is 0, whereas R minus I, remember R is 6. 6 minus 4 would be 2. So obviously the minimum is 0. So we fill in the value of 0 there. Make sense? So that's really what we need to really think. So if I were to write this code, I would say if I is less than R, then P of I is actually the minimum, basically this P of I is equal to minimum of P of I prime and R minus I value, right? But if this palindrome, I mean, now the next thing we need to do is move the I to 5 here, right? And you continue doing the same formula because I is still less than R. So you would assume to be the minimum value of P5 would be same as P1. You're gonna think about it. But if I is still less than R, you also need to check the value of R minus I, which is 1. So in this case, both of them are 1, so you would assume it is 1. But if I were to expand beyond R for some reason, right? We basically what we need to think is if this palindrome expands beyond R, we would update the C, the center, to be I now. You get it? Because remember, this is where when we did the original center, the maximum we were able to find was here and here. If for some reason that we were able to find that there was something more that matches on the other side, then the center moves. Okay. So that's really the consideration, basically, right? That is pretty much it. Um, but one point I want to mention is, why did we go for this? Why did we go for if I less than R, right? The reason is, if I were to be, if you were to expand this beyond this, there's a possibility that C would have already found it before, right? Like for example, if this was here and you were looking at this value and there is a B matching B, you know for sure that the next one matches because you already found it, right? So if you now go further beyond, then there's a possibility is that only to move the C to the next one and not necessarily that you could find more on this side. So really what we're saying is, why can't the palindrome center at I expand after R? If it did, it would have already been covered with the current center C. Okay, so that is why we are saying P of I is R minus I. So I think that's kind of what I was trying to explain. I stopped at these two formulas, but I think I forgot to add the if statement and minifying them too. So really, this is what I want to try to explain. So now at this point, P of I would be 5, but then when you see now your I, you can see that the center expands here, C and C. So that means your length is increasing. So you would move the R here, you would move the C to I here, right? And this will be 2, but then you continue on that effort. Now you'll say, okay, let's check A, and then let's check the other side. Where was I? Yeah, here. So now this would change to 3, right? That'll be the length there, and the L would be changed to this, and R would be changed to this, right? Now you compare, where was I? I was here, this and this, this and this, this and this. Now I compare B with B, so now this length will change to 4, right? And then the L would change here, and the R would change here. But then later on, you'll find out that this is not the same as this at the point you stop, and this will be your center. So basically, Maneker algorithm helps you find the center. And now the length will be, it is 4 plus 4, 8, 8 plus the 1 character, that is 9. So the length of the maximum palindromic substring is 9. Hopefully that helps. I will post this out to the video, and if you have any questions, we can chat later. All right.